The last video of today, part B.3, Introduction to Asymptotic Notations. In this part, we will learn those very compact and very concise, abstract, highly abstract notations. All right. First, let's consider limits of two growth functions. So we use several examples. So L'Hopital's rule, how to calculate the limits. But here, we look at the general cases. If we consider the limits of two growth functions, what are all the possible cases do we have? So let me try to list all the possible cases. All right. You can see we have these four cases. The first one, limit 0. The second one, limit equals non-zero constant c. C cannot be 0. So we separate 0 and non-zero numbers. The third one, infinity. Because infinity, we cannot treat it as a number. Infinity is not a regular number, so we should treat it differently. The last one, other than the first three cases, there is a last possible case. What's that? The limit does not exist. The limit does not exist. Okay? Yeah. The first three cases, we can treat the limit exists, right? Yeah. Even if the case 3, we can describe the limit infinity, right? But case number 4, the limit does not exist. All right. For all these 4 different cases, we need to have some special descriptions for the growth functions. All right, so here, let us look at the comparison results when we have these 4 cases. What are the conclusions for these 4 cases? All right. The first one, conclusion is order of growth of f of m, the numerator function over denominator function, when n goes to infinity, the limit is 0, you can see which one grows faster, right? Which one? Denominator function grows faster. So we say order of growth of f of n less than order of growth of g of n. Yeah, so we get a comparison result. Yeah. Case number 2, this time non-zero constant. We know when we compare our running time function, the constant proportional, remember that? The specific value of that constant is not important. If we only need to know 2 functions are proportional by certain non-zero function. So here we have the same situation. When the ratio of these 2 functions tend to non-zero constant, we say they have the same order of growth. Same order of growth, proportional, right? Same order of growth. Case number 2. Case number 3, we know order of growth of numerator function is higher, larger than that of the denominator function. So we have this conclusion. The last one, limit does not exist, then we don't know what the conclusion it is. The conclusion could be different things, right? Yeah. So we don't know. We don't know. So we need to think about it. Yeah, later we try to answer this question. Limit does not exist. How can we so first, it's not the first case, not second case, not the third case. Yeah. So that case, we cannot compare two growth functions, or the comparison of two growth functions cannot give us any helpful information. Yeah, so that's the situation. Yeah. All right. Yeah. So next. All right. So let's look at the next thing. Yeah. Because here, when we compare two growth functions, we need to use the limit technique. Limit, we know it's a calculus technique, the tool we can use. But the question is, the limit tool may have some limit. It may not always work. So the limit technique has its own limit. Sometimes it does not work. So we have this kind of situation we need to consider. Yeah. So the limit way has some limitation. So what's that? Because we need to worry about case number 4. How do we study case number 4? Right? Yeah. So we need a new method. We need a non-limit method for case number 4. Non-limit method for case number 4. Yeah. Okay. Yeah. But you may ask me, I cannot imagine under what situation you have case number 4. Right? The limit does not exist. So people cannot quite imagine case number 4. Here, I may like to give you a simple example. All right, so let me give you this example here. Okay. All right. Two functions. The first function how about that? Okay. 3 plus -1 to the nth power, parenthesis, times n squared. Okay, all right. The second one, 2 minus n plus 1 squared. How about that? Can you tell me what is the limit of this one? You can try. Can you tell me what is the limit of this ratio? Let me tell you, the answer is does not exist. Okay? The limit does not exist. But under this situation, we can compare the growth function, these two growth functions. Which one has higher growth order, which one has smaller order of growth? We can still compare. So we in this case, we cannot use the limit technique. Yeah. So we have to find a non-limit method. Yeah. So that's what we need to do. Next, objective. Yeah. Even if the limit does not exist, we can still compare growth functions. The question is how to do it. Yeah. All right. So before we go there, so let's look at the first three cases. We can use some very compact notations to describe the first three cases. The first one, little o notation. If we get case 1, we can use this notation. F of n belongs to little o of g of n. That notation. Okay? Little o of g of n, we can treat it as a set of functions. A set of functions. Large number of functions that satisfy the condition. If you take the limit of that function over base function g, the limit goes to 0. That's the definition of little o notation. Similarly, case number 2, we can write big theta notation. Big theta notation. F of n belongs to big theta of g of n. Very compact. The meaning is clear. We do not need to use a lot of words to describe it. Very neat. Very concise. Very abstract. Okay. Number 3, f of n belongs to little omega of g of n. Little omega of g of n. So 3 asymptotic notations. So we're using here. Yeah. All right. Next. So let's continue our non-limit based comparison method. Yeah. How do we compare two growth functions without using the limit technique? Yes, we have one. Okay. The one that is using upper bounds and the lower bounds. Inequality, upper bounds, lower bounds. Then we can still do appropriate comparisons. Okay. All right, how to do it? Yeah. First, usually the g of function, the one that we use at the denominator, usually simple function. Because when we use the simple functions, we have immediate idea how fast they grow. Right? Here, look at the example. And we know how fast n function grows. N square function grows. We know, we have some impression on that. N log n function, how fast it grows. Okay? So at least we can draw graphs for these simple functions. Okay? Yeah. So here I do not need to draw it. Yeah. All right. Next, the function f of n could be a complex function. Yeah. So usually the numerator function relatively more complex. So then we use a simple function to, try to measure it. Try to, compare with a simple function. Then we can use a simple function to describe a complex function. So that makes sense. Yeah. All right. Use some constant multiple of that denominator simple function, g of n, to approximate f of n. constant multiple. So here, the main method is here, using constant multiples. How to use constant multiples? Specifically, can we find two positive constants, C1 and C2? Positive. Cannot be zero. Must be positive. Cannot be negative. Must be positive constant, C1, C2. One for lower bound, another for upper bound, such that this inequality holds. So f of n greater or equal to C2 multiple of g of n, and less than or equal to C1 multiple of g of n. Between, in that way, then we have idea on f of n, right? So that is the new, that is the non-limit based method we mentioned before. All right. So this method works no matter the limit exists or not. That means if the limit does not exist, we can use this method, because we never need to touch that limit thing, right? We never need to touch the limit. But even if the limit works, we can still use this method if you like it. If it is simpler, we can still use this method. But because when we use the limit technique, remember we have that L'Hopital's rule. It is very powerful. L'Hopital's rule, very powerful. Derivative, using derivatives to calculate the limit, very powerful. So that means the limit technique has its advantage. So we need to use that limit technique sometimes. All right. At the end of this video, I want to talk about another important notation. It's called big O notation. So what is the big O notation? So this is another commonly used asymptotic notation. Definition is this. For a given function g of n, the notation big O of g of n represents the set of functions f of n satisfy certain conditions. So what kind of condition? The following condition. This condition pretty long. Let me explain this long condition. There exists some positive constant c, also positive, and some non-negative integer n0. Here, there is a special reference point. N0 is some important reference point, such that f of n less than or equal to c multiple of g of n for all n greater or equal to n0. So this is our reference point. When n value, the problem size, is greater than this reference point, then f of n function can be bounded from above by c multiple of g of function. Okay? So here you can see in two things I want to point out. The first one, we only consider upper bound. For this big O notation, big O, we do not consider lower bound, only upper bound. Okay? We don't care the lower bound. Okay? All right. So that's the first thing. The second thing, this reference point n0. you have freedom to choose this reference point. Because in our definition, it is not specified how to choose reference point n0. So you have freedom to choose it. Choose a good one. Choose a convenient one. Okay? But there is one requirement. Although you have freedom to choose that n0, but as soon as you select it, it must be fixed. After you make your first choice, then you cannot change it. Yeah. You have to stick with it. Yeah. For the whole procedure. Okay? Yeah. So you have one chance to choose it. So be careful to choose that. Yeah. All right. So for that kind of special reference point n0, yeah, we say sometimes we may not mention that n0. We can use this kind of vague wording. What kind of vague wording? When n is sufficiently large. That's a vague wording. What do you mean sufficiently large? The meaning is this special reference n0 point. Yeah. In the next, because this is already the last video of part B, in the first video of part C, I want to use graphs to explain the role of this reference point n0. Yeah. All right, so let us finish our part B video sequence right here.